2009, and then at the University of Manchester, and then he started his first postdoc in Excellence Cluster Universe in Munich, and then he moved to Korea and then spent some positions in Korea, and then since 2020 he is now leading the cosmology group in Asia Pacific Center for Theoretical Physics in Korea, and he will be talking about the topology of the large-scale structure. And let's welcome Stephen.
Thank you. Yes, thanks for the introduction. Thank you very much. So thank you for also inviting me, Tepe and Jensen. I really enjoyed it. It's my first time in Taiwan, and I really loved it. Very nice. I'll need to go on a diet when I go home. But so I work on cosmology. So there's a lot of cosmologists in the audience. There's also a lot of non-cosmologists in the audience, I think. This is a colloquium, so I'm going to try and introduce my topic in a way that try and captures the basics of cosmology and also topology and large-scale structure. So I'm going to try and make this self-contained and explain everything within this talk. I have a bit less than an hour, so I hope I can do that. If you have any questions, then please just stop me and I'll do my best to answer them. I might not be able to answer them immediately, but we can also talk after the talk. Okay, so this is the overview of my talk. So I'm going to start with an introduction, and the introduction is going to be very broad. It's going to be an introduction to cosmology. So I guess the cosmologists can just open their laptops here and just do their work. So this will be about half of the talk here, this introduction to cosmology and large-scale structure. And then the second half of my talk, I'm going to introduce the particular statistics that we try and extract from galaxy catalogs, which is, in this case, the genus. We actually have many different statistics we use, but I'm going to focus this talk on the genus, and I'll explain what that is, and then I'll explain how we use the genus to generate a standard ruler. I'll explain what that is, and how we get parameter constraints from this statistic. And then, if I have time, I'll just explain what we plan to do in the future to improve our analysis. But the first half of this talk is just a very broad introduction to cosmology. So I'll start here. So cosmology, I like to describe cosmology as built on a series of assumptions, and so we may as well start right at the beginning. So the first assumption is that the dynamical evolution of the universe is described by general relativity. Okay, so these are the Einstein equations. So this is the Einstein tensor, this is the energy momentum tensor, and this is just a system of differential equations. Okay, so this is just a differential operator acting on the metric g. So schematically, this is just the second derivative of g, the metric, and the first derivative squared. So this is a nonlinear system of partial differential equations, and this is just the energy of your system. Okay, so the system that we're trying to describe is the universe. Okay, so in principle, this is very simple. Okay, so all we have to do is say, well, what is the universe made of? What is it composed of? And we know kind of what that is. We know that it's made of photons and stars and hydrogen, dark matter, photons, and all the rest. So in principle, we can just input this the distribution of energy and momentum into the right-hand side of the Einstein equations, which these act as a source which curve space-time, solve these differential equations, and we're finished. That's obviously not that simple, which I'll show shortly, but it does beg the question, what is the universe made of? Okay, so this is what we think the universe is made of. So these are the 7 cosmological parameters of the standard cosmological model. And this is what we think the universe is made of at the present time. So we think it's around 5% what we call baryons, which is just basically hydrogen, stars. That's basically it. For the intents and purposes of this talk, this is just hydrogen. The dark matter is around 25%. We don't know what that is, but we know it only acts gravitationally, again, to intents and purposes. And the rest is in dark energy, which again, we don't know what it is, but we think that it's a cosmological constant. So it's a vacuum energy which causes to accelerate the expansion rate of space-time at the present time. So this is what we think the universe looks like today. This is what we think the universe looked like if you evolve it backwards to the cosmic microwave background. When the universe was 300,000 years old, it's currently 14 billion years old. And so this is just to show you that the fractions of the dark matter and the dark energy and the hydrogen varies as a function of redshift. As you look backwards in time, you're looking at different snapshots of the universe, and what energy component is dominating at different times depends on where you are in redshift. Okay, so this is the present time, and you see we're kind of dominated by dark energy with some dark matter or total matter, But at early times, as you go backwards, you start to become dominated by radiation, and you have this epoch of matter domination. So this is kind of like the time evolution of your components of your universe, but actually we need to know the spatial distribution, and that's where it gets complicated, because this is a very old simulation. This is from 2011, but it's not important. So this just shows you the evolution of dark matter from a very high redshift, so very early times when the universe was like 0.1 gigayear old, through to the present. And this is, initially you have this very almost perfectly homogeneous distribution of matter, but what happens is there's these very small fluctuations in the early universe, and these are from quantum fluctuations in the primordial universe, and matter falls into those gravitational potential wells, and you get an increasingly complicated distribution of matter as you evolve from the early times to late times. So we're evolving the simulation forwards in time. This is only dark matter, but it shows you the point that you end up with this very complicated pattern. This is called the cosmic web. It's a three-dimensional structure. You see these knots, these local overdensities, and you see matter falling into them. And you see filaments here, and it's hard to see, but these filaments exist on walls. Okay, so this is a locally anisotropic pattern of matter in the universe. This is what we actually observe through galaxies, and characterizing this distribution is extremely complicated. Okay, so we can't just input some complicated distribution of matter into the Einstein equations and get a full solution. So what we have to do is we make another assumption. Okay, and the other assumption, the second assumption I like to talk about, is that the universe on large scales is statistically isotropic and homogeneous. Okay, and so what that means, so isotropy, so this is a distribution of matter. Okay, so this is a simulated matter. Let's say we have an observer in the center of this distribution, and he points, or she points a telescope in some direction in the sky. And so isotropy tells you that statistically, the statistical properties of the matter distribution in this direction on the sky is the same as this direction. So it's basically a rotational invariance of your matter distribution. That's what isotropy means. And then homogeneity means that if you place an observer at different points on a spatial hypersurface, okay, they will measure also statistically the same properties of the matter distribution. So we have an observer here, and then we shift that observer by some constant in a spatial direction. He or she would observe the same distribution. Now these are assumptions. We can't necessarily test these exactly, because with isotropy, as we increase the area on the sky that we're looking at, the distribution will approach, or should approach, some constant value. Okay, so there should be smaller fluctuations as you average over larger scales, but you only have a finite area, so you can't ever tell exactly whether you observe an anisotropy that is a statistical fluctuation that you would expect, or whether it's an intrinsic anisotropy on this scale. And homogeneity is even harder to test, because we only ever have one observer, which is us. We have no other spatial points at which we can make observations at the same point in time. So this is very much an assumption that different observers on the same spatial hypersurface will measure the same statistical properties of matter. But these are assumptions that we make, and we do that because it makes things very simple. Okay, so because what we can do now is simplify the Einstein equations a great deal. This is the metric that satisfies the statistical isotropy and homogeneity on large scales. It's just time coordinate. So there's different ways of writing this. It's just the simplest. And we just have a single function a of t, which is the expansion rate of your spacetime. Okay, and then you have these spatial sections here, which are just flat. Well, I've assumed they're flat here for the purposes of simplification. They can be curved, but it doesn't matter. But this metric here is just invariant under constant shifts in your spatial directions. So if you add c to these will remain invariant. And if you write this in an angular coordinate system, this metric is invariant under angular rotations. Okay, so this is the FLRW spacetime. And a of t is the scale factor, and this describes the expansion rate or contraction rate of your spacetime. And you can insert this metric into your Einstein equations, and you get a very simple system to solve one effectively ordinary differential equation for the scale factor. And if you look for the properties of the energy momentum tensor, which satisfy these same approximations of isotropy and homogeneity, they reduce to, let's say, perfect fluids. So you just have an energy density, which is just a function of time, and some pressure. So this extremely simplifies your the properties of your spacetime, okay? But that is just the background spacetime, okay? So what we're saying is that on very large scales, if we average out all of the fluctuations that we observe, we just get what's left is just an expanding or contracting spacetime in the limit where there's no fluctuations. But we want to describe large-scale structure, okay? So that's not good enough for us. We have to do better. So now we go to the third assumption that I like to talk about, which is you have this, so this is a kind of a caricature of the universe and the expansion of the universe. So we start at some very early inflationary epoch. There's some primordial quantum fluctuations in this regime, and they get classicalized as the universe expands. And then that ends up with almost perfect energy density, almost perfectly smooth energy density in the early universe with very small fluctuations. And those small fluctuations grow with time because matter infalls into these gravitational potential wells, and they form the structures that we observe today via gravitational collapse. So that is the process of structure formation. So we can describe the initial condition of the fluctuations, okay, and this is an assumption made in inflationary models, okay. So the simplest inflationary models in the early universe predicts that fluctuations in the early universe are Gaussian random fields with small amplitudes. So that means if you have an energy density rho, this could be matter, this could be photons, this could be baryons, and you look for the initial time, so early times t, you have an average density rho, which is only a function of time, as I said earlier, because of isotropy and homogeneity. And then you get these small fluctuations delta, which are explicitly functions of space, okay? And the approximation is that delta here, this density perturbation, is much less than 1, and any velocity associated with the density is much less than the speed of light. And this is true at high redshifts, okay, so it's actually true at much higher redshifts, so 1,000 and down to 100, down to 10. It depends on the scale that you're looking at. And why are these interesting? So I really want to specify what a Gaussian random field is, because it will be useful later on in the talk. So for a Gaussian random field, okay, all your Fourier modes are independent and all the phases are randomly distributed. So if you take this density field delta here and you take the Fourier transform of it, you have an amplitude of that particular density in that Fourier mode, which is this, and we have a particular phase. And the phase is just some random number. It contains no information for a Gaussian field. Okay, it's just random on 0 to pi. And the amplitude contains all of the information, and this is just normal distributed with 0 mean assumed, and the variance of this amplitude is just equal to the power spectrum of your field, okay? So what that tells you is that, another important point is that each one of these Fourier mode amplitudes is independent and uncorrelated with the others, okay? So each Fourier mode is independent. And so what that tells you is that in the early universe, all of the information in your density fields is contained in the power spectrum, or in the two-point function, which is the Fourier transform of the power spectrum, okay? So in the early universe, physics is very simple, perturbations are small, everything's Gaussian. But what happens, as I'll show shortly, is that at later times, so what happens is matter infalls into these gravitational potential wells, and this is gravitational collapse, and it occurs over a very large timescale from redshifts of thousands to the present. It takes a long time for these things to grow. And initially, we're in the linear regime for a long time, but as we evolve further and further, eventually gravitational collapse is a nonlinear process because the Einstein equations are nonlinear, and that nonlinear process couples Fourier modes, and that makes delta, this density perturbation, non-Gaussian at late times. Okay, so that means that all the information is not just contained in the power spectrum of this field. And so there are 4 regimes relevant to cosmology, and I'm only going to talk about some of these today. So I already explained that if you go to homogeneous and isotropic background, so you smooth your density field on the largest scales, you just have this density perturbation delta goes to 0, and your total density of whatever this is, photons, baryons, dark matter, just becomes a function of time. And then if you go to slightly smaller scales, okay, but still very large scales, you're in a regime where you can do linear perturbation theory. And in that regime, your density perturbation delta is very small, and your average density, your total density is still approximately your average density. But then as you go to quasi-linear perturbations, so as you start to go to increasingly small scales, your density perturbation delta will grow, and you start to get these the explicit dependence on x on your spatial position, and this becomes non-Gaussian here. So this density field delta is non-Gaussian in this regime. And then you go to fully nonlinear, where this density perturbation is very large. This happens at very late times on very small scales. Okay, and this regime can only really be described by doing simulations. Okay. Now I'm only going to talk today about the background expansion, linear perturbations, and quasi-linear perturbations. Okay, so I'm only going to focus on regimes where we can do perturbation theory approximately. I'm not going to talk about the fully nonlinear scales. So by restricting ourselves to perturbation theory, we're looking at very large scales, so scales larger than any object that has virialized in the universe. So we're looking at scales beyond cluster scales. We're looking at tens of megaparsecs. Okay. So we don't have to worry about things like baryons. Okay, so this is just showing you very quickly what happens and why the field goes nonlinear at late times. So this is just this is really a simple picture. This is not how we do modern perturbation theory, but this is called Eulerian perturbation theory. So what you do is you write down your Einstein equation. Okay, so what? So you write down your density field, okay, which is your average density plus some perturbation. You write down your metric, which is the FLRW metric, which is just this scale factor A, and you have this this metric potential. Okay, this is the perturbation in the metric, and then you write down your Fourier modes. Well, we don't write Fourier modes for now, but anyway. So this is the 0,0 component of the Einstein equation. Practically, there's other terms, but we neglect them, so they're small. So this just looks like a Poisson equation. So this is the gradient squared of the metric potential, and it's just proportional to the density perturbation. This is a linear equation relating the metric potential and the density perturbation. And then these are the fluid equations. Okay, these are fully nonlinear. Okay, so this is basically the conservation of matter. Okay, so this is what you get if you put in the energy momentum tensor and take the covariant derivative of it. This is the 0 components. So this just tells you that the density field is conserved, and it relates the density time derivative of the density to the velocity. And this is the generalization of F equals ma. So this is giving you the rate of change of the velocity of this fluid related to the gradient of your potential. So this is these are the equations we have to solve. And you see they're nonlinear. Okay, so you have this term here, which is a nonlinear contribution. It's delta multiplied by the velocity of the field. And this term here is also nonlinear. It's the velocity multiplied by the gradient of the velocity. So if you look at regimes where this density field is small, then this term can be neglected, this term can be neglected. You have a series of linear differential equations, and when you take the Fourier transform, then each mode will evolve independently. So you just have basically delta of delta k, and you have some time evolution, but they completely decompose. But when this delta term starts to become large, when your density perturbation grows, because this matter is infalling into the gravitational potential wells, it's actually this term goes nonlinear first, and this term explicitly couples Fourier modes, because when you take the Fourier transform of this term, this is a product in real space, so it's a convolution in Fourier space, and this generates additional information in beyond the simple Gaussian statistics. So we can just look at this. Okay, so this is let's just look at a density field. So this is a simulation run, I think last year or 2 years ago maybe. This is Horizon Run 5, which was run at Kios, where I used to work. This is a hydrodynamical simulation with a gigaparsec box length and 100 megaparsecs. So it's kind of like a cone, a very long cone, where you have cosmological scales over on one dimension, and then 100 megaparsecs in the other 2 dimensions. So this simulation was designed to look at the cosmological effects on small-scale physics, so you need a very large box. And we generate a density field, so this is a dark matter distribution, but then we generate a density field from that by smoothing it. And this is what the matter distribution looks like if you take a slice of that density field at redshift 200. So this is at very early times, where you're just in pure matter domination. Everything should be linear, and everything should be Gaussian at redshift 200. And that's what you find. This is the density map. So the red points here are overdensities above the average density. The blue are underdensities, And this is what a Gaussian random field looks like, okay? So it's symmetric, so if you flip the overdensities and the underdensities, you get statistically the same pattern on the sky. And this is what we think the early universe looked like. But if you evolve to redshift 2, so this particular simulation evolved to redshift 2, this is what you get. So this again is dark matter only, and this is smoothed on very small scales. But what you see is the gravitation, the effect of gravitational collapse is for matter to infall into the local overdensities. So what you're left with is these large void-like regions, and then these very small, very high dense overdensities. Okay, so the overdensity delta here can be of order of hundreds on these scales. And so this is obviously completely non-Gaussian. Okay, you can see by eye that it's not, it's lost its symmetry. Okay, with respect to plus minus delta. If you if you multiply delta by -1, you get a completely different field, and it's completely non-Gaussian. Okay, and so this is the kind of field that we're going to be looking at within the galaxy distribution, and this is what we are going to try and extract information from. Okay, I'll skip that. So how do we do that? So what we typically have is a point distribution. Okay, so this is an example of a galaxy catalog. This is the SDSS. Okay, so each one of this is an overhead projection of a galaxy. This is actual data of a galaxy catalog. So each one of these is a galaxy. As a function of redshift, we're an observer at the center. And what you can do is you can extract the endpoint statistics from this. Okay, so the endpoint statistics are basically the excess probability of finding a galaxy at a certain separation. Okay, that's the 2-point function. So what you do is you just look for an excess probability that 2 galaxies are lying at separation r relative to some random distribution, and that tells you the extent to which galaxies are clustered due to gravitational collapse. And if you are looking at a Gaussian field, then this is all of the information you can extract from that field. But as I said, because this field in the late universe that we observe through galaxies is non-Gaussian, you actually have additional information in the endpoint functions. So for example, the 3-point function is the excess probability of finding 3 galaxies in a particular triangular configuration. Okay, so that's the 3-point function. This is the Fourier transform of this, which is the bispectrum. And for a Gaussian field, this is exactly 0. For the late-time galaxy density field, this is non-zero. And you can continue. The 4-point function is the excess probability of finding 4 galaxies in particular polyhedral configurations. So the goal of large-scale structure, or the goal that we use for large-scale structure, is to extract information from the point distribution using some statistic such as the endpoint functions. And this is an example. So this is the power spectrum. Okay, so this is the P of K, this thing here, of the SDSS. This is the luminous red galaxies. So there's 2 different galaxy catalogs here. There's the luminous red galaxies as the main galaxy catalog. And this red curve is the expectation value of this statistic from lambda CDM, and the black points are the measured values of these statistics from the data. And once you have so if you're doing perturbation theory, and we're focused only on perturbation theory, okay, so in that case, the power spectrum is the starting point, okay, so the power spectrum is this quantity here. But if you're doing higher order perturbation theory, then from the power spectrum, you can predict the bispectrum, for example, which is just the power spectrum squared multiplied by some function of Fourier modes. You can calculate the trispectrum, the 4-point function, by looking at products, triple products of the power spectrum. Okay, so once you have the power spectrum, you can extract all of the the further endpoint functions from your field. So a lot of those details aren't important particularly. So I'm just going to show. I'm basically going to summarize basically what we do in a nutshell, and that is we take a galaxy catalog, which is a point distribution. We extract some statistic. Okay, and this statistic could be anything in principle. As long as we understand how to predict what that statistic should be within the context of some cosmological model. In this case, this is the power spectrum. And then if we understand how this theoretical curve responds to certain cosmological parameters like omega b, the baryon fraction, the cold dark matter fraction, we can constrain the model, this red line, with these data points and obtain parameter constraints on things like the matter fraction. Yes?
I don't know if my question is quick. If it's not quick, you can tell me after.
Okay.
But can you tell me about the importance of sky coverage to having the width?
That's a really long question. I can, so I'll answer that question soon. The short answer is the impact of the size of the footprint and the angular selection function is huge on these statistics, particularly on the 2-point function. For example, it couples modes together artificially, and it generates you lose power on scales. It really depends on the statistic, and the statistic I'm actually going to show is not dependent on the mask at all. But the 2-point function and the 3-point function, 4-point function, forget it. It's a big job to remove the effect of the mask. So typically, what people do is actually they measure the convolved statistics. So they measure they don't measure the true power spectrum. They measure the power spectrum convolved with the mask, and then they take their theoretical curve and they convolve the theoretical curve with the same mask, and then you're comparing like for like. But I'll show you the statistic I use is not is independent of the mask. The laser pointer's gone. So is there a stick or something I can use? Ha. Good. Okay. So this is the step. Okay. And so what's going to happen, what I'm going to show you now is the statistic that we use, which is different from the 2-point function. But before that, I'll just show you some galaxy catalogs. Okay, so here is just some galaxy catalogs that are currently available for use. So there's some old galaxy catalogs, there's some new galaxy catalogs. So I'm just going to show you them on the sky, what they look like. And so each galaxy catalog is a point here, and it's as a function of the area on the sky that galaxy catalog occupies and the number density of spectra per square degree. So cosmologists want to be up here because we want large sky coverage, so we want to be almost all sky, but we want very dense samples so we can look at very small scales, so we can resolve very small scales for, we get more Fourier modes. So typically cosmology has evolved along these lines. Okay, so this is basically the number of redshifts that you obtain in your spectroscopic galaxy sample. So the early redshift galaxy catalogs are very low. There's only around 1,000. We're currently up to around 1 million redshifts per galaxy catalog. It obviously depends on the catalog, and sometimes people go very narrow in their sky coverage, but very deep, so they have a large number of spectra. So this is 2MASS. Okay, so this is the local galaxy distribution on the sky. Each one of these points is a galaxy. Each color is the redshift of that galaxy. You can't really see it, but this goes from redshift 0 to 0.07. Okay, so it's very low redshift. Then we go higher. So this is 2DF. Okay, so this is now an overhead projection of the galaxy distribution. You see this pattern, this highly nonlinear, non-Gaussian distribution of points. This now goes out to redshift 0.2. And this is the galaxy catalog that I will be looking at later. So this is BOSS. Okay, so this is this goes out to redshift 0.4, or even further to 0.6, and it's mostly red luminous galaxies. Just to show you really briefly that the future's bright for spectroscopic surveys. So we currently have now DESI data. It's not currently public, but they released their first results this month or last month. So DESI is what's called stage 4. Okay, so it has very high redshift, very dense samples, almost all sky. And so this is the sky coverage of the current DESI data. So it will cover this entire range here. So north sky, south sky, it has two different regimes. And from that, they measured the baryon acoustic oscillation, which I'll talk about later. And there's already plans to extend DESI, okay, to increase the areas, the sky coverage. And DESI 2 is being studied, will be proposed, and they will look deeper in redshift. And then there's even further, Spec 5, which will go to very high redshifts. Okay, I'll skip that. Okay, so now I'm going to start talking about specifically the work that I'm doing. Okay, so but just before that, I'm going to explain just what we do. So there's two different methods. So when you have a spectroscopic galaxy survey, okay, you have three pieces of information of each galaxy. You have its position on the sky in terms of RA and DEC, and you have its redshift, okay, which is a proxy for distance if you know a cosmological model. And so what you can do is you take your redshift catalog and you generate a three-dimensional density distribution. And we do that sometimes, but for the purposes of this talk, what I'm going to talk about is tomography, which is where you take your three-dimensional data and you bin it in redshift to generate a series of two-dimensional maps, and you study the evolution of the properties of these maps. Okay, so instead of taking three-dimensional data, we take successive slices of redshift data and study the two-dimensional information. So that's what we're going to do. We're not going to use 2MASS, we'll use BOSS, but I'll show you that later. So this is going back to my original plot. So here we have the point distribution, okay, and then we have some statistic that we want to measure from the data, and we have the constraints we get at the end. And for the purposes of the rest of this talk, I'm going to talk to you about the genus, which is the particular statistic that we use at KIOS. So what is the genus? So the best way to describe the genus is just with pictures. Okay, so this is another simulation of data. This is just this is Coyote simulation. This is just dark matter only. This is just a one slice of a three-dimensional distribution of dark matter. Okay, so again, you see this particular pattern, this non-Gaussian pattern. And so the data that we measure is a point distribution, but what I've talked about so far are fields. So we want to generate from that point distribution a smoothed density map, and you do that by smoothing. Okay, so this is a Gaussian smooth density map of this point distribution. I think this is smoothed at 10 or 20 megaparsecs, so it's cosmological scales where perturbation theory can be used. Okay, so now we'll get rid of the point distribution because we don't care about it anymore. And so this is the map that we're going to look at. And all we're going to do is we're going to draw a perimeter of constant density. Okay, so we're going to imagine that this is like these are hills, these are peaks in some kind of density distribution. These are minima. Okay, these are sort of valleys, and we're going to take a slice of constant density, and we're going to start at a very high densities, and we're going to move down, and each time we're going to cut this density field. And where we make that cut, we generate these perimeters of constant density. And the genus is just the number of connected regions made by this cut minus the number of holes made by this cut. I don't know if that's clear or not, but and we do this for many different values of the density. Okay, so this is what we do. So each time we define a constant density value, we cut this two-dimensional density plot by that value, and you get this one-dimensional perimeter. And each time we count the number of connected regions, so the number of regions above this density cut, which are these red regions here in this case, and you subtract the number of holes. Okay, so this is a hole, for example. This whole thing is one massive connected one massive hole which we take. This is a hole here, and the genus is very simple. It's just the number of connected regions minus the number of holes. And we do that as a function of density. So we repeatedly make that measurement as a function of density. And this is the result. This is what we get at the end. So this is the genus, so the number of connected regions minus the number of holes as a function of your density cut. So as you take your density cut, move it from high density to low density, each time you repeat this measurement of your density field, and you get this curve. So this nu is just the density, the constant density value that you choose to make this cut, divided by the root mean squared value of your field. Okay, so this is just normalizing. Yes? We do it in 2D. We also do it in 3D. So you can do both, and we do both. But today I'm only going to talk about the two-dimensional.
How do you decide the size?
In 3 dimensions. In 3 dimensions, it's hard to. This is why I like to talk about 2 dimensions, because it's easy to show. In 3 dimensions, you can imagine that each of your pixels has a color, and each time you select a density value corresponding to that color, you only select pixels above that density value. So it's like selecting 3-dimensional pixels based on some additional criteria, if that makes sense. And you generate a constant surface of 2 dimensions. I can show you. I've got some 3-dimensional stuff later. But anyway, so this is known as the genus curve as a function of density threshold cut. Okay, so each one of these points is one of these selections where we generate this constant surface this constant perimeter. And you can so you can understand what we're doing here is we're basically we're basically measuring the curvature of this boundary, because each time you go around this boundary, okay, if you imagine you have a normal to this boundary, each time you rotate once around a hole, you go around 2 pi in direction. And because the boundary is directed, so you go anti-clockwise around holes and clockwise around connected regions, you're going plus 2 pi every time you go around a connected region, minus 2 pi every time you go around a hole. So that's basically what we're measuring each time. And this is the result. So this is the genus curve that we get from 2-dimensional slices of galaxy data.
Is this sensitive to how you smooth the density field?
It is. So yes, I'll get to that. Yeah. So you can imagine that each time you smooth your density field, you're looking at, so the physical scale that you smooth at determines the physics you're looking at. So if you smooth on like megaparsec scales, you'll be able to resolve like clusters, for example. So, and you'll be able to resolve very strongly filamentary structure in your density field. As you smooth on increasingly larger scales, this field becomes Gaussian, because on very large scales you don't have non-linear gravitational collapse won't dominate, so you'll still be in the linear regime. So this effectively goes from a Gaussian field to a non-Gaussian field, and I'll show you shortly what that does to this genus curve. So the shape of this genus curve changes depending on what scale you smooth.
Are you going to give us some feeling about this curve?
About what it's sensitive to.
What does it say?
What does it say? Yes. Good. Exactly. So that's what we measure. Okay. So we've taken a point distribution, and then we've measured some statistic, a summary statistic. Okay. And so now we'll talk about what that summary statistic tells us about cosmology. So this is the definition of the genus. Okay. So as I described earlier, this is the curvature of that boundary. You have a bounding perimeter. This is the curvature, and you're just integrating over this one-dimensional perimeter. So this is an integral over your boundary, dq, of the curvature, and we've divided by the total area which the data is contained within. So you can rewrite this. Okay, so you can rewrite this line integral as an area integral. Okay, so this is just trivial. So now you have an integral over your whole space, and this is your delta function. So this is just picking out your perimeter of constant density. So this is just picking out pixels, if you like, where your density is equal to your some particular threshold nu. This is the Jacobian of this transformation. It's not important. And this kappa is the curvature of this integral, integrated over dA. So you can recognize this as just the area average. Okay, so this is just this quantity here integrated over your space. So this is the area average of this thing which I've just called G, where G is just this delta function, gradient of delta times kappa. And kappa is the curvature of your bounding perimeter, and you can just write that in terms of the first and second derivatives of your field. So this is the curvature of this bounding perimeter. Delta 1 is your derivative, so you have 2 dimensions. So this is gradient with respect to one direction, 2 directions, and these are the second derivatives. And so what we're measuring is a one-point function, okay? So you can imagine if you pixelate your density field, which is what we're doing, this is just a sum over pixels where you've discretized your field and you've discretized this function g. So this is just this one-point function, this sum of this quantity over your pixels. And so what we do in cosmology is we use ergodicity. This is getting a bit complicated now. But so ergodicity tells you that what we measure in cosmology is always a volume average. Okay, so when we measure the 2-point function, we measure all points that are separated by a certain distance and take the volume average of that in your space. And that gives you some volume average of a single random realization. And what we do in cosmology, or normally implicitly, is we equate that volume average to an ensemble average. Okay, so the ensemble average of a statistic is that particular statistic integrated over its probability distribution. Okay, so what we measure in cosmology is a volume average, or an area average in this case. What we can predict from theory is an ensemble average, which is just the quantity that we measure integrated over phi, which is the probability distribution of the variables. So that's a bit of a crazy jump. I'm not sure everyone's going to go with me on that, but that's what we do. Okay, so this is what we always do in cosmology. Normally it's implicit, but now I'm trying to show you exactly what it is we do. Okay, so if you know what the probability distribution is of your variables, then you can calculate this, okay, and then we can equate the ensemble average to the volume average. And as an example, okay, your probability distribution, if your field delta is Gaussian, that means the first derivative of your field is also Gaussian and your second derivative is also Gaussian. That's a property of a Gaussian distribution, okay, and so then you have a joint probability distribution phi, which is just this multi-dimensional Gaussian. You can integrate that exactly, and this is what you get. Okay, so this is the genus curve you would measure if you could measure the dark matter distribution at redshift 100. Okay, so if you are in a regime where you could do linear perturbation theory, this is what your genus curve would look like as a function of your threshold, your density. And this is the ensemble average. This is the probability distribution that I just said that you integrate out, and it is given by this here. So this is just an exponential in your density. This is just a Hermite polynomial. This, don't worry about that. That's just new. So there's no information contained in here. This is just the density. This is just the exponential of the density of the Gaussian, and all of the information in a Gaussian random field is contained in the amplitude of this function.
Still,
Yes.
sorry, so where does smooth scale information come?
Here. So all of the information is contained here, and what these quantities are the cumulants of the field, the 2-point cumulants of the field. Okay, so this sigma 1 and sigma 0 are just integrals over the power spectrum, and the power spectrum has been smoothed with a Gaussian of smoothing scale Rg.
But this smoothing scale is arbitrary, but I think this statistic is very sensitive to nonlinearity. So you should choose smoothing length.
Yeah.
Minimize,
So yeah, I'll get to that. So this is the limit where you're in the very large scales. Okay. So what I'm saying is, my point is that this particular shape of the genus comes from your probability distribution. Okay. So you take this, you input some probability distribution, and in this case I'm inputting a Gaussian. So what I'm assuming is all of your fields are Gaussian. So you must be in the linear regime to do this. And in that case, your genus looks like this. Okay. So this is what the genus would look like. Now.
Can I ask a question?
Sure.
So in what sense is this assumption non-trivial? Why does it have to be mentioned? I can't see like why could it break down?
Why could what break down? The amplitude.
So there's the classical notion of ergodicity being like time average equals space average.
Mm-hmm.
That's not the sense that it's used here, right?
This is not a time average. I would say this is an average over it's an average over states. Okay, so this is just each quantity weighted by the probability at that state. And so the caveat, I mean, that's a really technical question, but this is here you've assumed homogeneity and isotropy. Okay, so what we measure is a volume average. What this is the probability of this value at one single point in your space-time.
Or spread out.
So the average that you measure is spread out. So you take a bunch of pixels, and all the pixels that are within some density threshold, you calculate the gradient of the density field and its curvature, and then you just sum them at different points. And that is your average. That's your area average. Okay. The ensemble average is if you take a single point, you have this. This is a stochastic variable delta, and so is the gradient, and so the second derivative. And so at that point, you just sum over all possible combinations of those three variables, or whatever variables, weighted by the probability of that state. And the trick is that you assume that your field is isotropic and homogeneous, which means it doesn't matter where you take this point. It could be anywhere in your space. Now that's not true for actual cosmology. So there's a subtlety there, because in redshift space, yeah, there are circumstances where that's not true in cosmology. But if your field is isotropic and homogeneous, it's true. Okay, so this is what John said. I've got 5 minutes. Oh. Okay, what, as Tepe said, we're not looking at a Gaussian random field, we're looking at a non-Gaussian field, okay? So what we can do is we can take this probability distribution of your density field, its first derivative, its second derivative, and you can expand it, okay? So this is called the Gram-Charlier expansion, and this accounts for the fact, this accounts for perturbative non-Gaussianity, okay? So here you have, to linear order, you have just this Gaussian probability distribution, but you have next to leading order, you get a contribution coming from the 3-point function, and then the next to leading order is a 4-point function. So what you can write down is your probability distribution for a non-Gaussian field as an expansion in these cumulants. Okay.
So sorry, this is not Edgeworth expansion.
It's the same Edgeworth practically.
This is early actually.
Is okay. Fine. Yeah. I was debating whether to which one to write. Okay.
Okay.
But the principle is the same, okay? So what we have is a probability distribution, okay? We have this, this statistic that we measure. We input this non-Gaussian probability distribution here, and what we get is the non-Gaussian corrections to the genus, okay? So this is what we measure, this is what we would measure the genus to be, a redshift, very high redshift, where the field is linear. This is the genus that we actually measure from galaxy catalogs, and you see it's been shifted it's been shifted due to the shape being changed by the non-Gaussian corrections to your field. Okay, so this is the Gaussian point, this is the Gaussian contribution, and it's just the amplitude of this function. But then this, the shape of this picks up corrections, and to leading order in some expansion in sigma, you get contributions coming from the bispectrum. So this is just the skewness of your field. This is 0 for a Gaussian field. It's not 0 in late times. Okay, and you get also 3-point cumulants related to the first and second derivatives of your field. So, and you can actually continue this to the 4-point function. This was done by Matsubara very recently. So the details aren't important. The point is that we're actually measuring the same thing as the endpoint functions. So we're measuring basically an integral over the power spectrum here, and then we have contributions coming from the 3-point function, the 4-point function, etc., etc. And these can be related to just integrals over the bispectrum, the trispectrum, the 3-point function, the 4-point function. And actually, so what I'd just like to say is actually the 4-point function actually renormalizes the amplitude, but this effect is very small at cosmological scales. So I'm just going to talk, I've got like 5 minutes. So I'm just going to mention what we do with the genus. So there's many ways in which we can use this. So one way is we can actually just measure, we can just measure the amplitude of this function and get an integral over the power spectrum. We know how the power spectrum varies as a function of cosmological parameters, so we can actually just reconstruct the power spectrum. There doesn't seem to be much point in doing that, but we could do that, and we could measure the 3-point function by measuring the shift due to non-Gaussianity in this curve. But what I'm going to talk about is the fact that, so the genus amplitude here is actually a ratio of these two cumulants, okay, sigma 1 divided by sigma 0, and these are these quantities here. These are just integrals over the power spectrum, p of k, just some integrals over Fourier space. It's not important, the details. And the power spectrum is the linear power spectrum, okay, so we're expanding in the perturbation series in the probability distribution, and this p of k is just the linear power spectrum. And the linear power spectrum can be decomposed into a redshift contribution. Okay, so for galaxy catalogs, this is the galaxy bias, the linear galaxy bias, which is just a function of redshift. This is the growth rate of matter, which is in linear, is just some function of redshift. And then you have the Fourier space contribution, which is the initial time power spectrum, the primordial power spectrum, and the transfer function. These are only functions of Fourier mode k. So because the genus amplitude is just a ratio of these two quantities, all the redshift dependence of the power spectrum just comes out of these integrals and cancels. And you can see that, and what that means is that the amplitude of the genus should be conserved with redshift. Okay? as long as we're smoothing over scales where you're in the quasi-linear regime where you can do this perturbative expansion. And you see these are actually measurements from the Quixote simulations. So this is the measurement of the initial condition of these simulations at redshift 127, so where everything is linear. So this is the measurement of the genus. And then at redshift 0, okay, smoothed at 20 megaparsecs, this is the genus that we measure at late times. And although this genus curve has been squashed significantly by non-Gaussianity, the amplitude has been practically unaffected by gravitational evolution.
Standard ruler means that this peak position doesn't shift.
No, it's that the amplitude is the same. So it's not the actual position, it's the amplitude. And you can extract the amplitude. So this is the expansion. So these are Hermite polynomials. Okay, so these are just polynomials in density. These are orthogonal. So you can just multiply. So you take your measurement of the genus, you multiply by h1 and integrate it over your density. You get this amplitude out. So you can extract the amplitude, and it's orthogonal to these contributions. It's not orthogonal to this one because this renormalizes. But as long as you're in a regime where that's small, it doesn't matter.
But if you look at that, you had a scale invariant power spectrum. The whole thing is completely degenerate with because of sigma 8, right?
Sigma 8, no, it's also insensitive to sigma 8.
Not a scale invariant, because then everything can be shift. I can shift any scale by a sigma 8 change.
It's not for scale invariant. That's not, yeah.
The whole effect comes from the curvature of your power spectrum.
Yes, exactly. So I'm going to skip a lot here. So I'll just end with this slide. So this is the basic principle, okay? So I'll do one more slide after this. So you take a galaxy sample at a low redshift, okay? And you measure your genus, and you smooth with a certain scale, and you divide by the area of your data. This is practically insensitive to cosmology, okay? It's practically insensitive to your distance redshift relation. Then you measure the same quantity, the genus, for the high redshift galaxy sample. And if you get your cosmology wrong in your distance redshift relation, then you get your two scales wrong, okay? So you're smoothing at a slightly different scale, and you're dividing your total data by a slightly different area. So systematically, you get two scales wrong. If your power spectrum is scale invariant, it doesn't matter because it would affect the scales the same way. But because your power spectrum is not scale invariant, you would see a slightly different effect if you get your area wrong compared to your small scale smoothing scale wrong. So what that does is it generates an artificial systematic evolution in your genus amplitude as a function of redshift. So this is all measured from the same data, but if you choose an incorrect cosmology, you find that your genus amplitude will systematically evolve with redshift because of the curvature of your power spectrum. So let me just show you the measurement. So we can use that to place a constraint on the equation of state of dark energy, basically the expansion rate of your universe. Okay, so you can place a constraint on the equation of state of dark energy and omega matter through this distance redshift relation. So what we do is we measure the genus amplitude of a high redshift galaxy sample. Okay, so for this purpose we use BOSS, so the galaxy catalog at redshift 0.5. And we also make the same measurement of the SDSS main galaxy sample, which is a very low redshift galaxy catalog. And you make this measurement repeatedly for different cosmological parameters. Each time you change your cosmological parameters, your measurements will shift slightly up or down, depending on whether you've got the cosmology correct or not. And you find the cosmology which minimizes the difference between this point, this low redshift data point, and this high redshift data. And the end result is a constraint on the equation of state of dark energy and omega matter. This blue curve is what we get if we just use the genus of these two galaxy samples. This tan curve here is the Planck data, the same constraint of W dark energy and omega matter, and this is the combined constraint. And we get a 10 or 15% constraint on the equation of state of dark energy, which is worse than the BAO. So this is the equivalent constraint on the equation of state of dark energy coming from BOSS. It's 0.07. This is from DESI BAO, which was released last month, and they get 0.05. Okay, so their constraint is better than ours. The reason why is because we have to use this low redshift data point to calibrate these high redshift, and so this is cosmic variance limited. but we hope to do better in the future. So I'll stop there because I've grossly run out of time. I'm very sorry. I'll just say that the topology of the galaxy distribution can be used as a standard ruler, and we can test the expansion rate of the universe. We need more data. We need more low redshift data and high redshift data to improve the constraints. We also need to improve the theoretical modeling. So we need to improve the redshift space distortion effects, higher accuracy. We can look at shot noise contributions, galaxy bias. Okay, so there's lots of work to do, but we've proved in principle that we can use the topology of the galaxy distribution as a standard ruler. Thank you.
Okay, we'll limit to a couple of questions and then we can continue during the coffee break.
Quickly, so related to various questions. So you modeled over sigma 8. So you said you can break generalisation with sigma 8.
Sigma 8 won't enter this calculation.
You said this standard is coming from amplitude.
No, it's coming from the amplitude of the genus, not the amplitude of the. It's coming from the amplitude of this function, not the amplitude of the power spectrum. So the amplitude of the power spectrum drops out, right? Because the amplitude of the power spectrum is just in this term and this term. So it's completely insensitive to sigma 8. It's sensitive only to, the curvature. Basically, because this is an integral over Fourier modes of k squared. This is just an integral over k, zero, k to the 0. So it's a slightly different scale. Yeah.
So in this plot, your very high redshift graph is assuming it's purely Gaussian?
This is a measurement, so this is not actually made any assumption. But yes, it is very highly Gaussian, but because the simulation itself is Gaussian of those redshifts. So this is not real data, this is simulated data.
But how much does this result rely on that being Gaussian? So there being no primordial non-Gaussian?
Yeah, so I mean, the level of primordial non-Gaussianity, that's a really good question, by the way, because it would affect the shape of this curve. And if there was primordial 4-point function, that would affect the amplitude. But the effect is very small. So we're actually trying to measure the primordial non-Gaussianity with these functions at the moment. The late time non-Gaussianity is much larger than that, so it's very difficult to measure.
One last question.
Do you have a sense for sort of how efficient this is in terms of capturing all the available information?
I think that's a difficult question. So, I mean, it doesn't collect. So the only way of collecting all of the information is to measure all of the endpoints that you can to whatever statistical precision you can. Right? The endpoints contain all of the information. This measures the cumulants, which are the endpoint functions integrated over the Fourier modes. So they're kind of like they contain like a significantly reduced amount of information compared to all of the information available. But what you can do is you can measure, like, for example, the 4-point function very easily, or these cumulants of the 4-point function very easily, and the 5-point functions. So you can measure a small amount of information from the higher point functions quickly. I mean, I don't know if you've ever tried to measure a 5-point function or a 4-point function.
I've never heard of 5-point.
Yeah. So it's not pretty, but yeah. So it's a difficult question to answer. But no, it doesn't contain all the information. It contains partial information on your fields. The only way to get all the information is to measure the endpoints or do some machine learning black box business compared to simulations.
Okay, let's close the official session and then you're free to start an unofficial one outside. Let's thank Stephen again.
So how did you treat